In this video, we're going to look at an introduction to solution methods for non-homogeneous differential equations. There are several different options here. In fact, this is a topic that we will return to in Chapter 3 in connection with Laplace transform methods. That will give us another option, but without using Laplace transforms, there's a relatively straightforward method called the method of undetermined coefficients that we're going to introduce in this section. The basic method is fairly straightforward, but there are a couple of twists you have to be careful about, and there's quite a bit of arithmetic and calculation involved. That's the main challenge here. So recall that a second order linear constant coefficient homogeneous dE has that form, and the general solution always has that form, as we learned in the previous section, based on the solutions of the characteristic polynomial. In this section, we're going to be looking at non-homogeneous differential equations, constant coefficient non-homogeneous differential equations. So the left-hand side is the same. So it's going to turn out to be the case that the general solution on these is going to be equal to the homogeneous part, which we found in the previous section, and any particular solution. So the whole game plan here in this section is finding a particular solution, essentially by making some educated guesses. So here's our first example of this type of problem. So we have a second order linear constant coefficient dE, which is non-homogeneous because we have e to the 2x on the right hand side. You always want to get in the habit of finding your homogeneous solution first. You will appreciate the importance of doing that shortly when we look at some more examples, but for now, just take my word for it. You always want to find the homogeneous part first. So for the homogeneous part, we find that part in the usual way by setting the right-hand side equal to 0 and writing down the characteristic polynomial, which factors here. So we have two distinct real roots. So in terms of the theory in the previous section, we're in case 1, and we can immediately write down the solution of the homogeneous dE as c1 e to the 3x plus c2 e to the minus 2x. So the only thing left to do here is to see if we can guess the form of a particular solution. Now, because we have an exponential right-hand side, it's reasonable to guess something like this for our particular solution, a constant multiple times that exponential. So that's what we're going to try here. So we take that guess and take the first derivative of that and use the chain rule, and the second derivative using the chain rule again. Then we take those expressions for y particular and the first and second derivative of y particular and plug those expressions back into our original differential equation, which we started off with. And that gives us this equation, 4a e to the 2x minus 2a e to the 2x minus 6a e to the 2x is e to the 2x. So we have a common factor of e to the 2x everywhere in this equation, which we divide out and simplify the left-hand side. And that gives us then minus 4a equals 1. So a is 1/4, which gives us our particular solution that we were looking for, minus 1/4 e to the 2x. And if you feel like it, you can check that by taking the derivatives that does indeed satisfy the non-homogeneous dE. So our general solution here of this non-homogeneous dE is going to be c1 e to the 3x plus c2 e to the minus 2x minus 1/4 e to the 2x, and that does agree with Wolfram alpha where I checked this. The idea here is if we had two initial conditions, we would then take our two initial conditions and use those initial conditions to solve for C1 and C2. We'll look at an example like that later. For our next example, we have this. Notice the left-hand side part is the same, so we've already solved the homogeneous part. But now we're working with 4x. For the right-hand side, it would probably be good for you to try and solve this on your own before you go on to the next slide in the video. You might have some trouble with your initial guess if you do try it. If you have any trouble at first, you might want to try looking for an initial guess in a little bit broader category of functions. So that's a hint if you do want to try this before you go on to the next slide. So this is the problem that we posed on the previous slide. This is the homogeneous part, which we found in example 1. Based on the given right-hand side, our first attempt might be to try something like this, a times x. If we use that for our guess, that would give us a for the first derivative and 0 for the second derivative. And if we take those expressions and plug into our differential equation, we get 0 minus a minus 6ax equals 4x. And then the coefficients of the constant term on each side, matching the constant terms on the left side and the right side, we get negative a equals 0, and matching the coefficients of x, actually there's a typo here, that should be 4. Minus 6a would be 4, matching the coefficients of x on both sides. So a cannot be equal to 0 and also be equal to negative 2/3. That's impossible. This system has no solution. And the takeaway from that is that tells us that we didn't use a correct initial guess. So we look for, in solution 2, we're going to try an initial guess in a little bit broader category of functions. Instead of ax, we're going to try ax plus b. The idea here is once we start taking derivatives, we're going to have constant terms showing up, so we account for that possibility right at the beginning. Then the first derivative is a, second derivative is 0, and then we take those expressions and plug those into our differential equation and get this equation. 0 minus a minus 6ax plus b is 4x. Next, we match the constant terms on both sides. So the constant term on the left side is minus a minus 6b. The constant term on the right side is 0. And we match the coefficients of x on both sides. The coefficient of x on the left side is minus 6a. The coefficient of x on the right side is 4. So that gives us 2 equations and 2 unknowns, which is fairly easy to solve here. A is negative 2/3. We immediately get by solving that last equation in the previous line. And then 6b would be 2/3. So our solution for b is 1/9. Taking those values for a and b and plugging back in, that gives us our particular solution, minus 2/3 x plus 1/9. So our general solution would be this here. The homogeneous part here is the same as before, plus the particular solution here, which we just found. And that agrees with Wolfram alpha. In example 3, we have y double prime minus y prime minus 6y is e to the 3x. Same left-hand side, so same homogeneous solution. Based on what we did in example 1, we might try something like this, a times e to the 3x. If we pursue the same method, take the first derivative of that and the second derivative of that, and then plug into our differential equation like we've been doing, we get 9a minus 3a minus 6a times e to the 3x is e to the 3x. So we're getting the equation 0 equals 1, which obviously has no solution. I would highly recommend you think about why that happened, because at first glance it seems like example 3 is just like example 1, but there is a crucial difference. And I would encourage you to think about that on your own. Maybe look in the book if you get stuck, if you need an idea about why this happened. I will discuss why this happened with this example and what we can do about it in the next video, but I highly recommend you spend some time thinking about that on your own first before you go on to the next video.